Welcome to The Explainer. Today, we're going to talk about something you probably never think about, but it's literally holding up your world. We're digging into the hidden science that stops our cities from sinking, foundation engineering. Yeah, it's the unsung hero of every single structure, from a tiny house all the way up to the tallest skyscraper.
All right, so to really get into this, let's start with a really simple question, one that, it turns out, has a fascinatingly complex answer.
I mean, you look at these incredible structures, right? They're reaching for the clouds, these huge monuments to human ingenuity. But here's the thing. The real battle against gravity, it isn't happening way up in the air. Nope, it's being fought silently, deep, deep underground.
And the answer, of course, is the foundation. You can think of it as this crucial link, this handshake between the immense weight of the building and the earth itself. Its whole job is to take all that concentrated force and just carefully spread it out so the ground can actually handle it without collapsing.
And let me tell you, this unseen hero does not come cheap. Getting the foundation right is so unbelievably critical that it can eat up to 30% of a building's entire construction cost. Just think about that. It's a massive, massive investment and something you'll probably never, ever see.
Okay, so before you can even think about building up, engineers have to basically become detectives. Their first mission is to figure out exactly what's going on down below. And this investigation, it is the most critical first step of the entire project.
You know, their whole mission really just boils down to answering two fundamental questions. First, what are all the forces this building is going to push down onto the ground? And second, what kind of soil or rock are we actually dealing with here? Simple questions, but the answers are everything.
And when we talk about loads, it's not just the static weight of the building itself. Oh no. Engineers have to account for, well, everything. We're talking about the people and furniture moving around inside. That's a live load. The immense force of wind trying to push the building over. The shaking from potential earthquakes. And even the pressure of the soil pushing back from the sides. It's a lot to consider.
So how do they handle all these different loads on all these different types of ground? Well, engineers have this whole toolbox of solutions. And a really great way to get your head around this is an analogy I love to use. Let's call it the giant's shoes.
Just imagine for a second that the building is a giant, a huge, heavy giant. The foundation? That's its shoes. And the type of shoe it needs depends entirely on the terrain it's standing on. You wouldn't wear the same shoes on solid rock as you would to walk through soft mud, right? Same idea.
So these giant shoes basically fall into two main families. First, you've got shallow foundations. These are what you use when you're lucky and there's strong supportive soil right near the surface. But if you're not so lucky, you need deep foundations. That's when you have to dig way, way down to find a solid layer to stand on.
A perfect example of a shallow foundation is something called a raft or a mat foundation. This is exactly like putting a giant snowshoe on our giant. What does a snowshoe do? It spreads your weight over a huge area so you don't sink. That's what a raft foundation does for the building. It lets it kind of float on top of weaker soil. But on the other hand, what if you're dealing with really soft, squishy soil on top? Well, that's when you need deep foundations, like piles. And if the raft was a snowshoe, then piles are like a set of massive football cleats. They're designed to punch right through all those weak, unstable layers and grip onto something solid, a firm layer of rock or really dense soil way, way down below.
So, you see, the whole game in choosing the right shoe for the giant is figuring out this one crucial thing. What is the absolute limit of what the ground can handle before it just gives way?
In the world of engineering, this has a name. It's called bearing capacity. And you better believe this is the single most important number in all of foundation design. It tells you, point blank, the maximum pressure the soil can take before it fails, and fails spectacularly.
Okay, now this is where it gets really interesting. You see two terms here. Engineers will first calculate what's called the ultimate bearing capacity. That's the breaking point, the maximum pressure the ground can possibly take before it completely fails. But, and this is key, they never design to that limit. Instead, they take that number and divide it by a huge factor of safety, maybe 2 or 3, to get the allowable bearing capacity. That's the safe number they actually use in their design.
And believe me, that safety factor is absolutely critical. Why? Because when you exceed the ground's bearing capacity, the failure isn't some slow, gradual process. No, it's sudden, it's catastrophic, and it tends to happen in a few very distinct ways.
For example, in really dense sand or stiff clay, you get something called a general shear failure.
This is pretty dramatic. A really clear failure surface forms under the foundation and the ground literally splits and heaves upwards on the sides. You can see it happen right at the surface.
Now in looser soils, the failure is maybe a little less traumatic, but it's every bit as dangerous. This is called a local shear failure. What happens here is the building settles a lot, but that bulging on the surface is much smaller, more localized right under the footing.
And finally, we have the most deceptive type of all, punching shear failure. This is what happens in very, very loose or soft soil. The foundation basically just punches straight down into the ground, almost like you're pushing your thumb through a piece of paper. The scary part? There's almost no heaving, no warning signs on the surface at all. It just sinks.
So, what's the takeaway here? The next time you walk into any building, your office, your home, a skyscraper, just take a second. Think about that incredible, invisible engineering happening deep beneath your feet. That unseen hero, that massive concrete shoe, perfectly chosen for the ground it stands on, silently winning its battle against gravity, day in and day out.